Welcome to this comprehensive lesson on solving various types of algebraic equations and inequalities. Today, we'll cover radical equations, polynomial equations, equations that are quadratic in form, absolute value equations, and absolute value inequalities. Let's start with radical equations. A radical equation is one where the unknown variable appears under a root sign, such as a square root or cube root. The general strategy for solving radical equations is, first, isolate one radical on one side of the equation. Second, raise both sides to the appropriate power to eliminate the radical. Third, simplify and solve the resulting equation. And finally, check all solutions in the original equation to reject any extraneous roots. Let's look at an example. Solve the equation square root of x plus 3 equals x minus 1. First, let's consider the domain. Since we're taking a square root, we need x plus 3 to be greater than or equal to 0, which means x must be greater than or equal to negative 3. Additionally, the right side x minus 1 represents a square root value, which must be non-negative. So x minus 1 must be greater than or equal to 0, meaning x must be greater than or equal to 1. Next, we square both sides of the equation to eliminate the radical. Square root of x plus 3 squared equals x minus 1 squared. This gives us x plus 3 equals x squared minus 2x plus 1. Let's rearrange to standard form x squared minus 3x minus 2 equals 0. Now we need to solve this quadratic equation. Using the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. With it equals 1, b equals negative 3, and c equals negative 2, we get x equals 3 plus or minus the square root of 9 plus 8, all over 2. This simplifies to x equals 3 plus or minus the square root of 17, all over 2. So our two potential solutions are approximately x equals 3.56 and x equals negative 0.56. However, remember our domain restriction, x must be greater than or equal to 1. So we need to reject x equals negative 0.56 as an extraneous solution. Therefore, our only valid solution is x equals 3 plus square root of 17 over 2, which is approximately 3.56. Let's move on to polynomial equations. A polynomial equation is of the form a sub nx to the power of n plus a sub n minus 1x to the power of n minus 1 plus a sub 1x plus a sub 0 equals 0, where the values are constants. The techniques for solving polynomial equations depend on their degree. For linear equations, degree 1, we simply solve for x. For quadratic equations, degree 2, we can use the quadratic formula, complete the square, or factoring. For higher degree polynomials, we might use factoring, synthetic division, or the rational root theorem. Let's look at an example of solving a cubic polynomial equation. Solve x cubed minus 4x squared plus x plus 6 equals 0. First, let's try to find at least one root using the rational root theorem. Potential rational roots are plus or minus factors of the constant term 6. So, plus or minus 1, 2, 3, or 6. Let's test x equals 2. 2 cubed minus 4 times 2 squared plus 2 plus 6 equals 8 minus 16 plus 2 plus 6 equals 0. So x equals 2 is a root. Now we can divide the original polynomial by x minus 2 using either polynomial long division or synthetic division. Let's perform synthetic division to find the quadratic factor, using synthetic division with 2 as the divisor. 1, negative 4, 1, 6 are our coefficients. Multiply and add down the columns. 1 times 2 is 2, negative 4 plus 2 is negative 2. Negative 2 times 2 is negative 4, 1 plus negative 4 is negative 3. Negative 3 times 2 is negative 6. 6 plus negative 6 is 0. The result gives us the coefficients of the quotient polynomial. 1, negative 2, negative 3, with a remainder of 0, confirming that x minus 2 is a factor. So our cubic can be written as x minus 2 times x squared minus 2x minus 3. Now we factor the quadratic x squared minus 2x minus 3 equals x minus 3, x plus 1. Therefore, our solution is x equals 2, 3, or negative 1. Next, let's explore equations that are quadratic in form. These are equations that may not look like quadratics at first glance, but can be transformed into quadratics using a clever substitution. The typical pattern is a times u squared plus b times u plus c equals 0, where you represent some function of x, like x squared or e to the x. The strategy is to, first, identify the substitution u equals some function of x. Second, rewrite the equation in terms of u. Third, solve for u. And finally, back substitute to find x. Let's solve an example x to the fourth minus 5, x squared plus 4 equals 0. First, we notice that this equation involves x to the fourth and x squared, which suggests a substitution of u equals x squared. Making this substitution, our equation becomes u squared minus 5u plus 4 equals 0, which is now a standard quadratic in u. We can factor this. U minus 4, u minus 1 equals 0. So u equals 4, or u equals 1. Now, we back substitute u equals x squared equals 4, which gives us x equals plus or minus 2, or x squared equals 1, which gives us x equals plus or minus 1. Therefore, our solution set is x equals plus or minus 1 plus or minus 2. Now, let's move on to absolute value equations. An absolute value equation involves the absolute value of an expression, which always gives a non-negative result. The key strategy for solving absolute value equations is if we have the form absolute value of an expression equals, where a is a positive number, then we split it into two cases, either the expression equals a or the expression equals negative a. If a is negative, the equation has no solution, since absolute values are always non-negative. Let's solve an example. Absolute value of 2x minus 3 equals 5. Since 5 is positive, we split this into two cases. Case 1, 2x minus 3 equals 5. Case 2, 2x minus 3 equals negative 5. For case 1, we get 2x equals 8, so x equals 4. For case 2, we get 2x equals negative 2, so x equals negative 1. Therefore, our solution set is x equals 4 or x equals negative 1. Finally, let's examine absolute value inequalities. There are two main cases to consider. Case 1, when the absolute value is less than a positive number. Case 2, when the absolute value is greater than a positive number. For the less than case, if absolute value of an expression is less than a, where a is positive, this means the expression is between negative a and a. For the greater than case, if absolute value of an expression is greater than a, where a is positive, this means the expression is either less than negative a or greater than a. Let's solve two examples to illustrate both cases. Example 1. Solve absolute value of x plus 2 is less than 3. Using our formula, this means negative 3 is less than x plus 2, which is less than 3. Subtracting 2 from all parts, we get negative 5 is less than x, which is less than 1. So our solution is the interval from negative 5 to 1. Example 2. Solve absolute value of x minus 1 is greater than or equal to 4. Using our formula, this means either x minus 1 is less than or equal to negative 4, or x minus 1 is greater than or equal to 4. Adding 1 to each part, we get either x is less than or equal to negative 3, or x is greater than or equal to 5. So our solution is the union of the intervals x is less than or equal to negative 3, or x is greater than or equal to 5. To summarize what we've learned today, we've covered 5 types of equations and inequalities: radical equations, which involve variables under root signs; polynomial equations, which can be solved by factoring or using the quadratic formula; equations quadratic in form, which can be solved with clever substitutions; absolute value equations, which we solve by considering two separate cases; and absolute value inequalities, which give us either intervals or unions of intervals. Remember to check for extraneous solutions with radical equations, and pay attention to domain restrictions when solving any type of equation. Thanks for watching.